Situated just over 4 light-years from Earth, is a star system that has fascinated scientists for ages. Cosmically speaking, Alpha Centauri is nearby, essentially our immediate celestial neighbor, but it persistently kept its mysteries hidden. Even as countless exoplanets were found orbiting far-off stars throughout the galaxy, our closest stellar neighbor yielded no discoveries whatsoever. Subsequently, the James Webb Space Telescope directed its golden gaze towards that luminous point. Concealed within the intense brightness, researchers observed an unforeseen phenomenon. A faint glimmer materialized next to the star, only to vanish moments later. Subsequent examinations revealed nothing but emptiness. Should a planet genuinely orbit Alpha Centauri, it appeared to have receded once more into an unseen state. The discoveries made by Webb in our nearest star system compel us to reconsider our methods for seeking planets beyond Earth. If you're prepared, please tap the like button, subscribe, and join us as we explore what the James Webb Telescope has unveiled on this occasion. During a cloudless evening in the southern sky, one particular star appears entirely unenigmatic. It neither glimmers indistinctly at the limits of perception, nor conceals itself amidst countless faraway stars. It radiates brightly and assuredly, as though perfectly at home. This illumination originates from Alpha Centauri, our solar system's nearest stellar neighbor. Within the vastness of space, proximity is an uncommon descriptor. Our galaxy extends for 100,000 light-years. The majority of stars we observe are situated tens, hundreds, or even thousands of light-years distant. However, Alpha Centauri is located merely a little more than 4 light-years from our planet. Should the Milky Way be scaled down to the size of North America, Alpha Centauri would occupy the identical city block. It represents a tangible location, not an abstract concept. It is our cosmic next-door neighbor, yet for nearly 100 years, it declined to reveal if it harbored any planets. Its quietude was precisely what rendered it so captivating. Over several decades, astronomers devised progressively advanced instruments for detecting planets orbiting faraway stars. Scientists mastered the ability to discern the minute gravitational pull a planet exerts on its parent star, manifesting as a slight oscillation in its movement, akin to a parent subtly adjusting their stance when a child tugs their hand. They also quantified reductions in luminosity when a planet transited a star, obstructing a portion of its radiance for several hours. Direct photographs were even obtained of enormous nascent worlds emitting a dim glow in infrared wavelengths. By the dawn of the 21st century, thousands of exoplanets had been identified, colossal planets surpassing Jupiter in size, terrestrial worlds marginally larger than Earth, systems featuring closely spaced inner orbits, and others with planets propelled deep into frigid outer zones. It appeared that planetary systems were prevalent, yet not in this location. Not within Alpha Centauri. The paradox possessed an almost lyrical quality. We were capable of pinpointing planets circling stars hundreds of light-years distant, stars whose emitted light began its journey prior to the onset of the Industrial Revolution. Nevertheless, our adjacent stellar system continued to be exasperatingly devoid of findings. This situation was comparable to mapping mountains across an ocean, while the small hill visible from your window remained obscured by mist. A portion of this explanation stems from the inherent characteristics of Alpha Centauri itself. It comprises not one star, but a stellar family. Its 2 main stars, Alpha Centauri A and Alpha Centauri B, orbit one another in a leisurely gravitational ballet, requiring approximately 80 years to conclude. Both bear resemblances to our Sun, particularly Alpha Centauri A, which is almost an identical solar twin in terms of dimensions and heat. Initially, such a resemblance ought to simplify the search for planets. Given our understanding of how planets coalesce around our Sun, it's conceivable they develop similarly around a virtually identical star. Conceivably, there could be terrestrial planets in temperate orbits, possibly even seas heated by recognizable solar radiation. However, the dual-star composition of the system introduces complexities to every aspect. Picture attempting to construct an intricate sandcastle as 2 powerful gusts of wind converge from opposing directions. The fluctuating gravitational pull between Alpha Centauri A and B agitates the protoplanetary disk of gas and dust from which celestial bodies emerge. Previously, theoretical models indicated that stable planet formation might be challenging in such binary star systems, not at least in the tranquil, organized manner characteristic of our own solar system. Furthermore, there's the issue of luminosity. Alpha Centauri ranks as the third most luminous star observable from Earth's nocturnal sky. While its radiance might captivate poets, it poses a significant challenge for astronomers. When aimed at an object as luminous as Alpha Centauri, telescopes engineered to discern subtle planetary indicators resemble cameras optimized for dim candlelight. There's a considerable risk of them becoming overloaded. Locating a planet in that region is akin to attempting to spot a snowflake floating across a powerful searchlight beam. The intense illumination not only obstructs visibility, but also saturates the detection equipment. It scatters and diffracts into intricate configurations, concealing any proximate objects. However, luminosity represents merely a fraction of the overall difficulty. Additionally, the system is in motion. Among all stars visible to the unaided eye, Alpha Centauri exhibits one of the most rapid apparent movements across our celestial sphere. Due to its proximity, its location perceptibly changes over time when viewed against the backdrop of more remote stars. This movement necessitates exceptionally precise calculation. Even a minute miscalculation, an inaccuracy less than the breadth of a human hair observed from several kilometers distant, can cause a telescope's aim to deviate sufficiently to spoil an observation. Furthermore, an additional complexity arises: perspective. Given that Alpha Centauri resides within the Milky Way's dense galactic plane, the region behind it is densely populated with remote stars and galaxies. Any dim light source observed close to the system might, in fact, be an unrelated celestial body situated much further away, perfectly aligned with our viewing angle. Differentiating an actual planet from a far-off galaxy demands painstaking examination. Consequently, for many decades, Alpha Centauri persisted as a mystery. Over the years, a few preliminary indications emerged. These were signals that initially generated enthusiasm but subsequently vanished upon more thorough investigation. In 2012, the discovery of a potential Earth-mass planet orbiting Alpha Centauri B was reported, only for it to be subsequently challenged as probable data noise. Expectations fluctuated, much like ocean waves crashing upon the coast. Concurrently, numerous discoveries were made in other regions. The Kepler mission by NASA demonstrated that planets are not uncommon anomalies, but rather frequent results of stellar genesis. Comprehensive inventories became replete with verified exoplanets. We identified super-Earths and mini-Neptunes. We also observed hot Jupiters grazing the surfaces of their host stars, and we charted planetary configurations. These systems were unlike anything previously conceived, yet Alpha Centauri itself remained unrevealing. That quietude holds a uniquely humbling quality, the closest stellar system resembling our Sun. Despite its prominence in our night sky and its astronomical proximity, its most basic characteristics remained undiscovered. Did it harbor worlds, or was it merely a pair of luminous stars circling one another in the vast emptiness of space? That inquiry bore an emotional significance surpassing mere scientific scope. For ages, Alpha Centauri has been envisioned by humankind as the initial foray beyond our solar system. Science fiction authors selected it as a target not merely for its exotic appeal, but rather because it was theoretically attainable. Should we ever master interstellar travel, Alpha Centauri would represent the sensible initial port of call. But what sort of port? A desolate stellar system devoid of planetary bodies offers one kind of narrative. A system with worlds, perhaps even habitable ones, offers another entirely. By the time the James Webb Space Telescope was launched, the implications seemed altered. Webb was more than merely another observatory. It represented the most potent infrared telescope ever constructed, situated remotely from our planet, at a point of gravitational equilibrium from which it could survey the cosmos in profound, cold silence. Webb was engineered to peer into the past, to examine the earliest galaxies and the atmospheres of remote exoplanets. It was designed for dim, ancient illumination, not for brilliant proximate stars. Nevertheless, scientists started to question if Webb could sufficiently obscure Alpha Centauri's brightness. If it could generate an artificial eclipse using its coronagraph, it might discern the thermal radiance of a mature planet. This would be the heat glow of a developed world stemming from thermal emission rather than reflected light. A world heated by its sun would emit a subtle infrared glow, akin to a rock holding residual heat after dusk. The concept was audacious, even perilous. Directing such a delicate apparatus at one of the sky's most luminous stars necessitated meticulous planning. The telescope's sensors were invaluable, beyond replacement. No one wished to jeopardize their integrity. The observation called for a level of precision exceeding standard procedures. Computations considering the star's movement, luminosity, and the disruption from its binary partner were essential, yet the payoff was exceptional. Should Webb prove successful, it would achieve an unprecedented feat for any telescope, directly investigating the area surrounding our closest sun-like star in search of planets. This endeavor alone signified a pivotal moment. Over many generations, Alpha Centauri represented closeness devoid of understanding, akin to a brilliant beacon whose coast remained hidden. Presently, for the very first time, humankind held an instrument able to gaze straight into its intense brightness. The issue shifted from merely conceiving of worlds in that location to whether we could ultimately observe them. As Webb directed its golden reflective surfaces toward that well-known star, the subsequent events would convert Alpha Centauri from a quiet celestial body into a paramount enigma within contemporary astronomy. The James Webb Space Telescope was not designed for direct observation of objects like Alpha Centauri. Rather, it was constructed to peer far back in time at extremely remote galaxies. The illumination from these galaxies commenced its voyage prior to the formation of Earth's oceans. Its reflective surfaces were meticulously refined to capture faint signals originating from the nascent cosmos. Weak infrared emissions, attenuated by eons of cosmic expansion. Every aspect of the telescope's construction prioritized frigid and tranquil conditions. Alpha Centauri, however, offers neither. It possesses intense luminosity, remarkably so. Its proximity ensures its light reaches us powerfully and without attenuation, overwhelming sensors with its brilliance. Directing Webb towards it resembled employing a night vision device to gaze straight into a stadium floodlight. The danger extended beyond mere technical malfunction. It involved complete saturation and overexposure. Irreversible harm could occur, so what was the motivation? The reason is that planets do not merely reflect light, they emit their own glow as they revolve around a star. It takes in energy and subsequently releases it as thermal radiation. Even a frigid celestial body, hundreds of degrees below freezing, still emits subtle infrared illumination. While imperceptible to human vision, this warmth becomes discernible to Webb, which is precisely calibrated for those specific wavelengths. The majority of exoplanets directly observed prior to Webb's operation were youthful and substantial. These planets continued to radiate intensely due to residual heat from their formation, much like embers that had not yet completely extinguished. However, Alpha Centauri constitutes an ancient system approximately 5 billion years old, mirroring the age of our own sun. Any celestial bodies present there would be fully developed, cooled down, and significantly less luminous. They would not radiate with the intense warmth of youth, instead they would emit a faint glow. To perceive that subtle emission, researchers utilized Webb's mid-infrared apparatus. This instrument, designated MIRI, functions at wavelengths, specifically around 15 micrometers, where colder entities exhibit the clearest luminescence. A celestial body possessing a temperature between 200 and 300 Kelvin, similar to the outer areas of our own solar system, gives off discernible radiation. Should a Saturn-sized planet revolve within Alpha Centauri's habitable region, MIRI could potentially detect it. Nevertheless, the intensely bright star remained a challenge. This is precisely where the coronagraph becomes essential. Fundamentally, a coronagraph functions as a simulated eclipse within Webb's optics. A minuscule occulting disk obstructs the star's core illumination, thereby diminishing its brilliance and enabling the visibility of dim, proximate celestial bodies. It cannot entirely eradicate the stellar light, as that is physically unachievable, but it lessens it sufficiently to unveil companions that are thousands of times dimmer. Picture yourself positioning your thumb over the sun in an attempt to spot a faint aircraft flying nearby. While you cannot obstruct every single light ray, you can diminish the intensity sufficiently to catch sight of what is in the vicinity. However, even utilizing this method, Alpha Centauri presented an unparalleled difficulty. In contrast to remote stars that seem nearly stationary in the firmament, Alpha Centauri exhibits swift movement. Its intrinsic movement, or its perceived traversal across the celestial dome, ranks among the most significant observed. While such movement might appear minuscule in common parlance, for Webb, accuracy is critical down to the millisecond. Even a minor mispositioning of the star relative to the coronagraph's mask could permit light to escape around its periphery, saturating the visual with undesirable brightness. To aim at Alpha Centauri, an unconventional method was necessary: indirect targeting. Rather than directly fixing on the brilliant stellar network, the telescope initially focused on a neighboring reference star with a more controllable luminosity. Upon achieving stability and precise orientation, the telescope executed a meticulously computed blind offset, adjusting its focus by a predetermined distance to position Alpha Centauri behind the coronagraph. This operation necessitated exact awareness of the star's location at that precise instant. Given Alpha Centauri's close proximity, it also displays parallax, which is a perceived change in its location resulting from Earth's orbital path around the Sun. Over the course of a year, its celestial coordinates subtly vary. Observations scheduled for 1 month would necessitate recomputed coordinates for a subsequent month. Each specific factor had to be taken into account: its intrinsic movement, the parallax effect, and its orbital dynamics within the binary pair. No element could be presumed to be stationary, and furthermore, there was the presence of the companion star. Alpha Centauri A is not a solitary luminous body. Its companion, Alpha Centauri B, orbits sufficiently near to interfere with observations. Even with Alpha Centauri, a perfectly obscured, light from B could disperse across the sensor, generating diffraction patterns and intricate halos. A single coronagraph cannot simultaneously obscure two luminous stars located at distinct positions. Researchers were compelled to model and subsequently remove the contamination, thereby distinguishing genuine signals from optical anomalies. The challenge was akin to attempting to discern a faint, distant echo amidst the cacophony of two nearby blaring loudspeakers. The initial endeavor was preceded by months of extensive simulations. Engineers evaluated various scenarios using software, forecasting the diffraction of light, the detector's reaction, and how extraneous noise might conceal a genuine signal. The team practiced the blind offset approach in a virtual environment prior to utilizing actual telescope observation time. The initial efforts proved to be less than flawless. The quality of the data was compromised. The positioning lacked sufficient precision. Light escaped in manners that diminished the instrument's sensitivity. However, the team honed their methodology. They modified the acquisition protocols to enhance the precision of centering. They engineered specialized data processing workflows tailored specifically for the intense luminosity of Alpha Centauri. Furthermore, they thoroughly characterized the instrument's performance under operational parameters it was never initially conceived to manage. The Webb telescope, constructed for the purpose of examining galaxies at the very limits of cosmic history, was now being extended into uncharted operational domains. This situation possesses a certain poetic quality. An instrument crafted to investigate the farthest expanses of the universe was now being employed to scrutinize the adjacent star. This scenario was comparable to a deep-sea submersible, built for exploring oceanic abysses, being unexpectedly tasked with charting the coastline of its home port. Yet occasionally, the most significant breakthroughs are not located at the periphery of exploration. Instead, they sometimes reside within the intense brightness of something well known. Upon the ultimate execution of the refined observation campaign in August of 2024, Webb maintained its gaze for extended periods. Protracted exposures gathered subtle infrared photons concurrently with the coronagraph, mitigating the dominant stellar nucleus. Information flowed back from its remote orbital position, situated near the second Lagrange point, a million miles distant from Earth. The initial data received did not appear encouraging. The unprocessed images presented a disordered appearance. Diffraction artifacts extended outwards, and dispersed light originating from Alpha Centauri B traversed the observational field. Intricate patterns of detector artifacts and noise intertwined. For an observer unfamiliar with the data, it resembled abstract artwork, a jumble of light and dark lacking discernible significance. Yet concealed within that seeming disorder lay valuable data. Researchers in astronomy employed a method known as reference star differential imaging. Through observing other celestial bodies in identical environments, they developed models illustrating the instrument's performance without planetary interference. These baseline patterns were then removed from the Alpha Centauri observations, systematically eliminating inherent characteristics progressively. Further computational procedures pinpointed and mathematically eliminated correlated noise formations, thereby isolating any persistent, distinct point-like features. This undertaking was deliberate, meticulous, and unyielding. Every stage resembled wiping mist from a pane, uncovering forms that had always existed yet were hidden. Subsequently, from beneath the subdued luminosity, a weak indication appeared. It was tiny, faint, situated precisely past the area of strongest stellar light reduction. A warm spot. The Webb telescope achieved what numerous individuals deemed unattainable. It peered into the intense brightness of the closest sun-like star and detected something that ought to have been exceedingly difficult to perceive. If that specific point signified a planet or something altogether different, remained a topic for future investigation. But at that instant, the instrument had demonstrated a significant truth. Alpha Centauri was no longer beyond reach. Its quietude had been disturbed. Upon the final assembly of the processed images, no one anticipated any dramatic revelations. The group had braced themselves for uncertainty, perhaps a weak indication, or possibly no detection whatsoever. Alpha Centauri had previously failed to deliver. Prudence was the prevailing sentiment. Initially, the information appeared as a tempest of illumination. Diffraction patterns radiated from the obscured star, while subtle lines from the accompanying star traversed the field of view diagonally. Remote stars shimmered like far-off metropolises beyond a luminous skyline. Visually, it was comparable to attempting to discern a soft utterance within a bustling basilica. However, the essence of astronomy lies not in initial visual perception, but in what persists once all other elements are eliminated. Progressively, the team deducted reference templates. They simulated the way stellar light curves around the coronagraph's obscuring device. They eliminated correlated interference that consistently showed up in calibration measurements. They scrutinized separate portions of the observation to ascertain if any characteristic endured, and then they perceived it. A dim, point-like origin, unwavering and clear. Situated approximately 1.5 arcseconds from Alpha Centauri A, it was neither spectacular nor brilliant, merely a modest, constant radiance in the mid-infrared spectrum. Although roughly 10,000 times fainter than its neighboring star, in astronomical terms, this is entirely sufficient. The indication achieved statistical importance. It was sufficiently robust to exclude random interference with exceptional certainty, making the probability of this being merely a detector variation exceedingly low. A tangible entity had left its mark within the information. The group tentatively designated it as S1, not identifying it as a planet, but simply as Source 1. Its observed distance equated to approximately 2 astronomical units from Alpha Centauri A, roughly double the Earth-Sun separation. This particular area lies close to the outer edge of the star's habitable region, where conditions might permit liquid water to persist on a solid planetary body. Judging by its infrared luminosity, the celestial body's approximate temperature ranged from 200 to 250 Kelvin, roughly negative 50 degrees Celsius. While chilly by terrestrial measures, this aligns with a gas giant heated by a solar-type star at such a range. Should the simulations prove accurate, S1 could be a world with a mass similar to Saturn, not a scorching Jupiter grazing its star's surface, nor a luminous, nascent planet emitting residual heat from its formation, but rather a venerable billion-year-old giant silently traversing a consistent orbit. If confirmed, this fact alone would render it historically significant. Historically, direct imaging techniques have preferentially detected youthful, substantial planets situated far from their parent stars. These worlds are readily observable due to their high temperatures and considerable orbital distances. S1 presented itself as more ancient, less hot, and significantly nearer to its parent star than nearly all previously directly observed candidates. Its detection was akin to noticing a faint porch lamp next to a brilliant beacon. An object. Its presence was considered too faint for detection at such a close range, yet prior to any rejoicing, the group needed to critically scrutinize their own finding. Each potential alternative explanation required thorough examination. Might it be a distant galaxy by chance positioned along our viewing path? Remote galaxies are capable of appearing as indistinct points of illumination. The area situated beyond Alpha Centauri resides within the congested galactic plane of the Milky Way, a place where misidentification frequently occurs. The researchers consulted various astronomical databases. No identified celestial body was found at that specific coordinate. Historical photographs from different observatories revealed no data aligning with the observed luminosity. Could it instead be a closer object? Perhaps an asteroid traversing our solar system during the period of observation? Objects within our solar system exhibit movement against the backdrop of more distant stars. Had this been such an entity, its location would have perceptibly altered throughout the observation period. However, it did not shift over many hours of data. The signal stayed fixed in relation to Alpha Centauri A. Might it be an instrumental artifact, a deceptive image generated by the device itself? Coronagraphs are known to generate intricate diffraction patterns under specific circumstances. Leftover speckles have the potential to imitate point-like emissions. In order to verify this, the group introduced simulated planetary signals into the unprocessed data and ran them through the identical processing sequence. Genuine signals exhibit distinct behaviors from artifacts in nuanced statistical manners. Its characteristics align more closely with those of the artificially introduced planetary signals than with mere instrumental interference. While it successfully cleared all internal evaluations, a sense of prudence still prevailed. Within the realm of science, a solitary observation serves as an initial step rather than a definitive outcome. Celestial bodies are in constant motion. Should S1 genuinely be in orbit around Alpha Centauri A, its location would alter across time in a manner consistent with gravitational principles. Kepler's laws preclude any planet from staying fixed in position. It is compelled to follow a curved path around its parent star. The precise form and velocity of this trajectory are determined by its orbital duration, eccentricity, and inclination, yet movement is an unavoidable certainty. Such movement would serve as the conclusive evidence. Should S1 reappear at a newly forecasted location, the argument for its planetary nature would be significantly bolstered. Should it fail to manifest or exhibit movement contrary to the principles of orbital mechanics, then the August observation would necessitate a fresh analysis. The group responsible for the discovery recognized this fact instantly. A blend of enthusiasm and circumspection was present. News of the detection would ultimately reach the media, but initially, the cosmos needed to be afforded a further opportunity to provide confirmation. Subsequent observations were slated for the beginning of 2025. The anticipation was uncomplicated. S1 ought to be present, potentially somewhat displaced along its orbital path, yet still discernible. Astronomical researchers conducted orbital simulations, investigating potential trajectories that corresponded with the August position. Orbits with brief periods would cause the planet to traverse rapidly, those with extended periods more gradually. Highly elliptical orbits would significantly alter the perceived distance between observation intervals. Numerous scenarios were conceivable, yet nearly all forecasted that S1 would persist in being observable in some manifestation. Concurrently, the ramifications began to extend widely. Should S1 prove to be genuine, it would attain the status of the nearest exoplanet candidate ever directly captured in an image. It would revolve around a star strikingly analogous to our own Sun. Its existence would be within a binary star system, a type of environment once considered unfavorable for planetary development. This final point held significant importance, as binary stellar systems introduce complexities to a planet's orbital stability. Alpha Centauri B's gravitational pull regularly disturbs the vicinity of Alpha Centauri A. Nevertheless, theoretical simulations have demonstrated the presence of stable regions within a few astronomical units of either star. The location of S1, approximately 2 astronomical units away, was precisely within the boundaries of that anticipated secure zone. Put differently, should a planet orbit Alpha Centauri A, this specific spot is precisely where its discovery would be expected. The observation appeared not merely credible but also aligned with theoretical frameworks. Despite this, the field of astronomy has a track record of challenging even the most diligent researchers. Indications that seem robust may dissipate upon further examination. Random interference can often be mistaken for genuine patterns. The cosmos is intricate, and even the most sophisticated instruments possess inherent limitations. The observations scheduled for February 2025 were poised to put everything to the test. Should it be detected once more, the enigma would evolve into a verified finding. Conversely, if it failed to reappear, a far more peculiar situation would emerge. For planets engage in numerous activities. They revolve, they emit light, they shed heat, yet they do not merely disappear. February 2025 dawned with a subdued sense of expectation. The subsequent observations were no longer experimental. The methodology had, by this point, undergone prior validation. The blind offset performed as intended. The coronagraph maintained its stability, and the data processing pipeline had demonstrated its efficacy. It possessed the capability to strip away layers of luminosity and expose what resided underneath. If S1 indeed constituted a planet, this particular juncture would serve as its definitive moment of validation. The James Webb Space Telescope was once more directed towards Alpha Centauri A. Its sensors were inundated with infrared radiation for extended periods. Light particles, having traversed interstellar distances for over 4 years, were intercepted and transformed into numerical data. This data then flowed continuously back to our home planet. Researchers commenced processing without delay. Initially, all observations appeared customary, characteristic diffraction patterns and lingering luminosity. What they observed was the recognizable disordered signature of a luminous star viewed via a coronagraph. The group applied the identical subtraction techniques, reference star comparisons, and principal component analysis that had previously unveiled S1 in August. Their attention was directed to the anticipated zone. However, nothing was detected. There was no faint point of light, no subtle indication of heat, nor any statistically meaningful sign. The search area was expanded. It was hypothesized that the planet might have moved further than predicted. Its orbital trajectory could have displaced it along a curved path, altering both its angular position and its distance. Computer models indicated a spectrum of potential new locations, yet nothing was found. The data was reprocessed entirely, with adjustments made to various parameters, different noise limits, and alternative methods for glare removal. Separate research groups independently examined the images to preclude any prejudice. The outcome, however, remained unaltered. S1 had disappeared. A distinct form of quietude descends after an unanticipated negative finding. It is not the stillness associated with failure, but rather the quietude of perplexity. The collected data was pristine, and the telescope operated without any issues. Its sensitivity levels either met or surpassed those recorded during the August observation. A planet with Saturn's mass was expected to be present according to models, yet the image displayed nothing but void. April offered a subsequent opportunity. It was possible that in February, the planet was in an unfavorable part of its orbit, positioned too near the star and partly obscured by its brightness. An additional few months could move it further away, making it visible once more. When April's data came in, the analysis was rerun, yielding no results. once more. The entity that had been detected with significant statistical confidence in August 2024 failed to appear in either February or April. For a brief period in 2025, the most straightforward conclusion seemed most probable. Möbius 1 had never actually existed. Even a 5 sigma detection, which is statistically robust by scientific measures, doesn't assure reality. Infrequent anomalies do occur. Measuring devices can generate spurious readings that initially pass various checks before being exposed as false positives. Throughout astronomical history, signals that were once hailed as discoveries were subsequently categorized as mere noise. However, certain aspects of this particular situation made that inference difficult to accept. The observation made in August exhibited consistent behavior across different, unrelated datasets. Unlike typical artifacts, it neither flickered nor blurred. Its characteristics aligned with what would be anticipated from a point source observed through the instrument's optical system. And yet, planets are not known to disappear. But do they? In an effort to comprehend the potential phenomenon, astronomers shifted their focus from the telescope itself to geometric principles. A coronagraph's observational capability is not uniform in every direction. Its detection sensitivity is determined by physical laws. Light curves around the mask's periphery. Due to diffraction, certain viewing angles offer greater clarity than others. Consequently, some areas within space function as effective blind spots. Picture directing a flashlight's beam through a narrow aperture. The resulting light is not entirely even. Distinct patterns emerge, such as more luminous arcs and fainter areas. A minuscule object traversing that light path could be visible at one point and undetectable at another, despite remaining unchanged itself. Should an object pursue a highly elliptical orbit, its separation from Alpha Centauri A would fluctuate considerably across different periods. When at its most distant point, known as a pastron, it would be positioned at its greatest separation. Its detection would become simpler as it approached periapsis. It would approach the star more closely, entering zones where the lingering stellar glare obscures the faint thermal signature of a planet. Under such circumstances, its vanishing would signify not its destruction, but rather its hiding. Serious orbital simulations commenced. Researchers produced thousands and subsequently millions of potential orbital trajectories that aligned with the August observation. They adjusted parameters such as eccentricity, inclination, orientation, and orbital period. Their inquiry was straightforward. How many conceivable orbits would allow a planet to be detectable in August 2024, yet concealed in February and April 2025? The outcome was astonishing. Over 50% of stable orbital arrangements yielded precisely that behavior. In these situations, the object would have been close to a pastron during the August viewing, sufficiently distant from the star to be discernible despite its brightness. By the beginning of 2025, it would have progressed inward along its elliptical trajectory, entering an area where the coronagraph's ability to distinguish objects falls below the necessary level for detection. The planet itself would remain in existence. The Webb telescope would simply be incapable of observing it. This potential explanation completely redefined the enigma. The planet's vanishing no longer conflicted with the planetary theory. Indeed, from a statistical standpoint, its non-detection in early 2025 was more probable than its sustained visibility. While numerous orbital solutions existed, the narrative became considerably more captivating. Back in 2019, prior to Webb's observations, astronomers operating the Very Large Telescope in Chile had detected a weak preliminary indication close to Alpha Centauri A. The potential object, designated C1, received no corroboration from observations made on Earth. Terrestrial observations are hampered by atmospheric disturbances capable of simulating planetary indicators. Nevertheless, the documented position of C1 was nearer to the star than where S1 was found in August. Could these possibly be the identical entity? Should a solitary planet traverse an elliptical path, it might have seemed closer in 2019, more distant in 2024, and subsequently concealed once more in 2025. Once simulations integrated both the 2019 suggestion and the 2024 discovery, the findings grew significantly more persuasive. A range of possible orbits accounted for both locations, simultaneously explaining the lack of detections during the 2025 subsequent observations. According to this scenario, S1 is not an apparition. Rather, it is an entity journeying on an elongated elliptical path, intermittently becoming discernible before receding behind the veil of stellar illumination. The characteristics of its orbit indicated something out of the ordinary. An eccentricity close to zero point 0.4, considerably more stretched than Earth's almost circular trajectory, and a revolution period spanning 2 to 3 Earth years. Its inclination was notably angled compared to the plane of the binary star system. This type of orbit would render S1 distinct from any prominent planet within our solar system. Furthermore, it would account for its disappearance at specific junctures of its trajectory. S1 would occupy the coronagraph's prime location, offering the best contrast. Several months afterward, it would migrate into areas where diffraction and lingering brightness prevail, rendering it practically undetectable even though it was still physically there. The observations conducted in February and April did not invalidate the planetary theory. Instead, they rendered it more enigmatic. This was because verifying it now demanded perseverance. Assuming the simulations were accurate, S1 would once more move further away, reappearing in an advantageous spot by mid to late 2026. A new opportunity would arise, providing another occasion to observe it circling its star. Should Webb observe Alpha Centauri within that anticipated time frame and locate S1 close to its predicted position, the evidence supporting a genuine planet would be conclusive. A stable, gravitationally linked path observed over several years would rule out almost every other hypothesis. Should it not resurface, the enigma will intensify yet again. Regardless of the outcome, the implications are immense. What started as a dim infrared light source has evolved into an examination of orbital dynamics, instrumental constraints, and human endurance. The planet previously thought absent might actually reside precisely where physical laws dictate, concealed in full view, awaiting the opportune alignment of its trajectory. To bring it back into sight, some 4 light-years distant, Alpha Centauri persists in its serene motion. It remains unaffected by the discussion occurring on a tiny blue planet that has only recently started to perceive with clarity. For a moment, let us hypothesize that S1 is genuine, not a variation, not a spurious signal, not a distant mirage, but an authentic planet circling Alpha Centauri A, our closest star resembling the Sun. What sort of celestial body would it be? The infrared luminosity, as gauged by the James Webb Space Telescope, provides our initial insights. At approximately 15 micrometers, S1 emitted thermal energy indicative of a temperature ranging from about 220 to 250 Kelvin. This equates to roughly 50 degrees Celsius, which is chillier than Antarctica during its winter, yet warmer than the upper atmosphere of Saturn. It is not a superheated hot Jupiter closely orbiting its star, nor is it a luminous nascent world emitting residual heat from its creation. It seems to be something more subdued, more ancient and colder, a fully developed gas giant revolving at a distance similar to that of Mars within our solar system. Its calculated mass is approximately that of Saturn, possibly ranging from 80 to 150 times Earth's mass, sufficiently large to accumulate a dense hydrogen-helium atmosphere, but not substantial enough to initiate stellar fusion. If verified, it would be a bona fide planet, and its position is what renders it exceptional. Alpha Centauri A possesses a luminosity marginally greater than our Sun, which consequently pushes its habitable zone further away. The area capable of supporting liquid water on a rocky world is situated at a greater distance from that star than Earth's orbital path is from our own. The estimated orbital path of S1 ranges between approximately 1 and 2 astronomical units, positioning it either close to or inside that temperate zone. Naturally, S1 itself could not support life, given that gas giants lack a firm ground below their upper atmospheric layers. The pressure rises without cease. From a space perspective, what appears to be solid ground is simply the uppermost atmospheric stratum. Upon sufficient descent, gaseous substances condense into unusual material forms. No oceans, no land masses, no stable footing exist. However, massive planets seldom journey in isolation. Jupiter, for instance, possesses over 90 satellites. Saturn boasts an even greater number. A portion are diminutive and uneven, while others constitute distinct celestial bodies. Titan features a dense atmosphere and fluid lakes, albeit composed of methane rather than water. Europa and Enceladus conceal planet-wide oceans under frozen shells. These satellites are far from sterile stones. Instead, they represent intricate, active settings. Picture now similar satellites circling Swan, heated not merely by internal tidal forces, but also by the consistent illumination from a star resembling our Sun. Should a sizable moon orbit within Alpha Centauri A's temperate region, it might acquire sufficient stellar radiation to sustain liquid water on its surface, provided its atmosphere was adequately dense. Rather than a frigid ocean confined under ice, liquid water could freely traverse its exterior. Cloud formations could develop, and precipitation might occur. Its firmament would feature two stars, Alpha Centauri A, luminous and golden, and more distantly, Alpha Centauri B, which is smaller yet remains discernible. This would result in subtle secondary shadows being cast over many decades as the binary pair's orbit gradually alters. This is no longer mere theoretical conjecture. It represents a physically credible situation. Should S1 indeed exist, the planet's irregular orbital path introduces an additional dimension of intricacy. Given an estimated eccentricity close to 0.4, its separation from the star would fluctuate significantly during every orbital cycle, particularly at its nearest point. S1 would absorb considerably more radiation when closest to the star compared to its most distant position. Such a fluctuation might induce extreme seasonal changes affecting not only the planet itself but also any satellites circling it. Climatic trends could alter over cycles spanning multiple years. Polar ice formations could grow and diminish. The chemical composition of the atmosphere might fluctuate in sync with its orbital cadence. No such system has ever been directly witnessed by us previously. Every exoplanet imaged to date has been youthful and distant from its parent star. They emit significant light, yet reveal scant information regarding developed, sun-like planetary settings. S1, if its existence is verified, would represent the inaugural directly captured image of a gas giant, billions of years old, situated within the habitable region of a star almost identical to our Sun. It would essentially serve as a reflection of our solar system's external areas, positioned merely beyond our galactic threshold. A further implication exists, less overt yet equally significant. Over many years, certain theoretical frameworks propose that stellar binary systems, such as Alpha Centauri, could face difficulties in developing stable planets within their interior zones. The gravitational force exerted by an adjacent stellar partner has the potential to agitate protoplanetary disks, thereby hindering the gradual accretion of matter required for world formation. However, if S1 is found precisely where models indicated only marginal stability, it would imply those models were insufficient. Worlds might possess greater robustness than previously supposed. Binary star arrangements, formerly considered inhospitable, could harbor numerous worlds. Furthermore, binary stars are prevalent. Approximately 50% of solar-type stars within our galaxy are found in multi-star configurations. Should planets be capable of forming and enduring in settings akin to Alpha Centauri, the count of prospective planetary systems throughout the Milky Way would increase significantly. This alters our view of the cosmos. The prevalence of planets is already established. Projects such as Kepler demonstrate that the majority of stars probably possess at least one planet. However, discovering a world orbiting our nearest sun-like star transforms the discussion from mere data to a more personal connection. This renders the concept concrete. Alpha Centauri is not merely an unnamed item within a list. It's a well-known star visible from Earth. It has served as a guide for sailors and has sparked numerous narratives. Within the foreseeable future, it represents the most plausible target for journeys between stars. Furthermore, it might now harbor a gas giant within its habitable region. This is significant because closeness alters every aspect. Being only 4 light-years away, Alpha Centauri is sufficiently near for subsequent generations to potentially dispatch probes there within a few decades. Initiatives such as laser-propelled light sails seek to attain speeds approaching that of light, quick enough to traverse that span in roughly 2 decades, should such a planet exist. These expeditions would possess a definite objective, a particular orbital path, a tangible world for detailed examination. Even in the absence of interstellar voyages, its closeness improves our ability to observe it. A world orbiting Alpha Centauri looks bigger in our night sky compared to planets orbiting stars located 10 times the distance. Its emitted light is more intense, and its orbital path is simpler to monitor. Enormous ground-based observatories, which are future telescopes, are presently being built. These will exceed even the capabilities of the Webb telescope. They might analyze the atmospheric makeup of S1 and look for indications of methane or water vapor. They could potentially even discern subtle signs of meteorological activity. Moreover, if S1 possesses substantial moons, sophisticated equipment could eventually deduce their existence via faint gravitational influences or fluctuations in luminosity. The entirety of this hinges on one unanswered query. Does S1 truly exist? Should it be real, then the cosmos has positioned a Saturn-sized behemoth in the most captivating conceivable spot around our neighboring star, accessible to both human creativity and future investigation. Conversely, if it isn't real, the enigma itself provides insights into the constraints of our tools and the intricate nature of light. However, what renders this juncture remarkable is that, for the first time ever, humankind has achieved the necessary observational precision to even pose this inquiry. Regarding Alpha Centauri, for hundreds of years, that star was merely a luminous dot. Subsequently, it evolved into a sun-like binary. Currently, it's a system we can investigate for distinct planets. Regardless of whether S1 turns out to be an actual world or an illusion, a significant boundary has been surpassed. We are no longer speculating about our closest stellar companion. Instead, we are actively researching it. And within that research, concealed by brightness, appearing through infrared heat, could reside the initial confirmed exoplanet beyond our solar system, near enough to eventually seem less like a far-off star and more like a place to visit. Within scientific inquiry, an enigma doesn't persist indefinitely. It becomes more defined following S1's disappearance. By early 2025, astronomers faced two main potential explanations. The detection in August 2024 was either an exceptionally uncommon optical phenomenon, or the planet had simply shifted to a location beyond the reach of present-day instruments. To differentiate between these alternatives, they resorted to forecasting. The force of gravity is not enigmatic. Should S1 be genuine, it is compelled to adhere to the identical principles that govern Earth's revolution around the Sun and Jupiter's orbital motion. Its trajectory cannot be arbitrary. Rather, it must follow a predictable arc through the cosmos. Furthermore, if that trajectory is sufficiently charted, it will indicate when the planet is expected to reappear. Computer models of its orbit pointed towards a critical time frame, the middle to end of 2026. Under numerous stable arrangements, S1 would once again move outward, heading back towards its apastron, which is the most distant point in its elliptical path from Alpha Centauri A. At that specific range, the planet would emerge from the most intense glare, entering the restricted time frame where the James Webb Space Telescope's coronagraph attains its maximum sensitivity. To put it differently, the cosmos has established a specific time. If S1 truly exists, its reemergence is anticipated. This forecast converts the enigma into something verifiable, no longer philosophical or speculative, but quantifiable. Should Webb scrutinize Alpha Centauri within that time frame and locate S1 close to its anticipated location, the evidence would be conclusive. This would involve 3 separate observations, one from Earth in 2019, another from space in 2024, and the final one from Webb in 2026. Once more, it would delineate a consistent orbital path. Arbitrary interference is incapable of mapping a gravitational ellipse over several years. Distant galaxies do not adhere to Kepler's laws when orbiting proximate stars. However, if no observation is made in 2026, if the region stays vacant even with advantageous positioning, then the balance shifts to the contrary conclusion. The observation from August would be reclassified as an infrequent equipment malfunction, essentially a statistical phantom that momentarily mimicked a planetary body. Regardless of the outcome, a significant insight will be gained. Should it be verified, SA1 transcends being merely a data point. It would represent the nearest exoplanet ever directly captured in an image. A fully developed gas giant situated in a temperate region, circling a star almost indistinguishable from our Sun. A stellar system sufficiently near for future telescopes and potentially even spacecraft to investigate thoroughly. Conversely, if disproven, the insight gained holds comparable significance. It clarifies the distinction between genuine data and false positives. It improves the methodologies necessary for capturing images of planets obscured by starlight. It enhances subsequent investigations targeting other proximate stars, as Alpha Centauri merely marks the initial step. The techniques devised for this particular observation, such as blind offset pointing, extreme contrast reduction, and improved noise modeling, are transferable to other locations. Other luminous nearby stars previously deemed too challenging might now become accessible. Every endeavor advances the boundary somewhat further. Furthermore, a more profound transformation is unfolding. Throughout the majority of human existence, stars were perceived as inaccessible points of light. Subsequently, they were recognized as suns, and later we discovered they harbor planets. Currently, we are starting to discern distinct planetary bodies, specifically around the closest ones, not solely by deduction, but via direct visual capture. This advancement alters our viewpoint. Alpha Centauri is no longer merely a luminous speck in the southern celestial sphere. It represents a system possessing inherent structure, exhibiting orbital movement, and potentially featuring geographical characteristics. It could harbor a gas giant, following an elongated trajectory every several years. It might contain moons heated by the illumination of two stars, or it could astonish us once more in unforeseen manners. Webb's accomplishment was not merely the detection of a dim infrared light source. Rather, it proved that our closest stellar neighbor can be explored with a degree of detail previously considered unattainable. The intense luminosity is no longer insurmountable. The tiny light source is now visible next to the powerful beam, and thus, the narrative now takes a break. Not at a conclusion, but rather at a period of transition between its vanishing and reappearance, between its initial discovery and subsequent verification. Approximately 4 light-years distant, should S1 genuinely exist, it proceeds along its orbital path uneventfully. Unaware of its designation or the discussions it has ignited across our small blue world, it merely obeys gravitational forces as it always has. When Webb observes again, the outcome will be unequivocal.